Hi everyone, good morning. Happy New Year. And I'm really grateful to be here, more so as the first speaker of 2020. So my name is Kang. This talk is about the fixed price approximations to optimal efficiency in bilateral trade. And this is joint work with Jan van Draak, who is in the math department at Stanford University. So our paper looks at the trade-offs between incentive compatibility, simplicity, and efficiency. The literature in mechanism design tells us that stronger incentive compatibility notions, such as dominant strategy incentive compatibility over such as Bayesian incentive compatibility, leads to the reduced efficiency of mechanisms. And likewise, if the mechanism designer restricts attention to simpler mechanisms, where mechanisms are simpler in some sense of the word, then this in general leads also to reduced efficiency of mechanisms. So one example that takes this to the extreme is the work by Morrison and Satterthwaite, who showed the impossibility result that first best efficiency in the bilateral trade problem is in general impossible to achieve even under the weak notion of Bayesian incentive compatibility. One thing that Morrison and Satterthwaite also show is that the second best mechanism can be difficult to design in this particular example. And by that I mean that the mechanism designer is required to have detailed distribution knowledge about the agent's types. So two questions arise from this. The first question is, how then do we design simple mechanisms, by which I mean mechanisms that don't rely on such detailed distributional knowledge, at least on the mechanism designer's part. And the second question is, how much efficiency do we then lose if we sort of restrict attention to mechanisms that are simple and don't rely on such distributional knowledge? And so in this paper, we study these two questions in the context of fixed price mechanisms in bilateral trade. So one question that you might have at this point is, why do we study fixed price mechanisms in the context of bilateral trade? We focus on the bilateral trade problem because it is a canonical problem in mechanism design. And given the incomplete information setting, where agents are only privately informed of their own values, the mechanism designer maximizes an objective such as efficiency, and this is pretty natural. Moreover, the work of Morrison and Satterthwaite show that the second best mechanism in this particular problem can be complicated to design. There are two levels of complexity. So the first level is strategic complexity, by which I mean that the second best mechanism of Morrison and Satterthwaite is not dominant strategy incentive compatible. The second level of complexity is informational complexity, by which I mean that the mechanism designer is assumed to know the entire distribution of agent types. By contrast, fixed price mechanisms are simpler for bilateral trade, and in particular, the work of Haggerty and Rogerson shows that the fixed price mechanism in this case, or fixed price mechanisms, are strategically simple, by which I mean that the mechanism is dominant strategy incentive compatible. And in fact, they show that essentially the only dominant strategy incentive compatible mechanisms are fixed price mechanisms, subject to some regularity conditions. In this paper, we supplement this view of fixed price mechanisms by showing that the optimal fixed price mechanism is not only strategically simple, but also informationally simple as well. And also, these optimal fixed price mechanisms, regardless of the distribution, achieves at least 1/2 of the first best gains from trade. So before I describe the model, let me start with a simple motivating example. So this is essentially the bilateral trade problem with a particular uniform distribution between 0 and 1. So to describe the problem, the seller has an indivisible good which the buyer wishes to buy. There are two agents in this problem. Each agent is privately informed of their own value. So the buyer has a value of B, and the seller has a value of S. And B and S are drawn from the identical distribution, which is the uniform distribution between 0 and 1. So in the absence of informational frictions, the first best mechanism allocates the good to whichever agent has the higher value. So in this case, it allocates the good to the buyer if the buyer has the higher value. Otherwise, it allocates it to the seller. And we can compute the expected gains from trade, which is 1/6. By contrast, the optimal fixed price mechanism here sets a fixed price of 1/2. And so the mechanism dictates trade if and only if the buyer's value exceeds the price of 1/2 and the seller's value is below the price of 1/2. And likewise, we can compute the expected gains from trade in this example, and it works out to be 1/8. So the point of this paper is that in this example, in the context of this example, 1/8 is not very different from 1/6, and in fact, it achieves 75% of 1/6. And this paper shows that this holds more generally for distributions other than just the uniform distribution between 0 and 1. Let me state the main contributions of this paper. First, it develops methods to show that fixed price mechanisms perform well even in the worst case scenario. So we'll extend the results from the previous example to show that it holds for general distributions, not just for the uniform distribution between 0 and 1. And moreover, our methods apply for different variations of this model. Second, we also explain why fixed price mechanisms are used in practice. So one example of a fixed price mechanism that's used in practice are dark pools in financial markets, where dark pools take as fixed prices the price in lit exchanges, and agents in dark pools trade by choosing the quantity that they wish to trade instead. So the two explanations that we provide in this context, the first explanation is that these mechanisms are simple to design. Namely, we just choose the price equal to the mean. In the previous example, it turns out that the optimal price of 1/2 is optimal because it's the mean of the uniform distribution between 0 and 1. And the second explanation that we give is that the optimal fixed price mechanism guarantees good performance, in this case, at least 1/2 of the first best gains from trade, and this guarantee is high if we know more things about this distribution. And finally, in the paper, but not in this talk, we also provide some guidance on designing fixed price mechanisms. Roughly speaking, in thin markets, such as the bilateral trade problem, where there is exactly one agent on each side of the market, using the mean of the distribution as the fixed price is approximately optimal, exactly optimal in the bilateral trade case. And in thick markets, where there are more agents on each side of the market, choosing the median of the distribution is optimal instead. And we also show that the worst case performance improves as the market grows. So we quantify how fast this performance improves. Good, so let me describe the model. The model is standard, it's the bilateral trade problem. There are two agents, a buyer and a seller. Again, the seller has a single indivisible good that she wishes to sell. And both agents are risk neutral and preferences are quasi-linear in money. The one assumption that we differ from the standard bilateral trade problem is that both agents have values that are drawn from the identical distribution F. So in the problem that Myerson and Satterthwaite consider, the buyer's value and the seller's value can potentially be drawn from different distributions. F here is assumed to have finite and positive mean. So let me talk about this assumption and why we deviate from the setting of Myerson and Satterthwaite. The assumption that we make is essentially one of ex ante symmetry. And this assumption is motivated by our application to financial markets, where the same market participants may either buy or sell, depending on their inventories. So our interpretation of agents in this problem are that agents are liquidity traders. These traders can either have unit demand, in which case they're buyers, or they have unit supply, in which case there are sellers. And the key assumption here, the only assumption that we're making, is that the value that these agents have for the asset is independent of whether they are a buyer or a seller. I would also like to say that we're not the first to make this assumption, and in fact, this assumption is standard in other models of financial markets. Okay, so back to the problem. The role of the mechanism designer here is that the designer chooses the fixed price mechanism. So the designer chooses a price P. P can a priori depend on the entire distribution F of agent values. And so the fixed price mechanism P dictates trade if and only if the buyer's value B is higher than the price P, and the seller's value is below the price P. And conditional on trade, the buyer pays the seller a transfer exactly equal to the price P. And the goal of the mechanism designer is to maximize the expected gains from trade. Here we denote the expected gains from trade by gamma. Gamma is a function of the price P as well as the distribution F. Okay, so our first result is a simple result, but it's a powerful characterization of the optimal fixed price mechanism. And we show that the optimal fixed price mechanism is such that the optimal price is exactly equal to the mean of the distribution of agent values. So the proof is pretty simple. It relies on one single observation, which is that via integration by parts, we can write the expected gains from trade, gamma p, in the form of this expression over here. The upshot of writing the expected gains from trade according to this expression is that we can compute the difference between the expected gains from trade under the optimal price, which is the mean of the distribution, denoted here by p star, as well as any other price p. Right? So we claim that this difference is always non-negative. If it's non-negative, then the expected gains from trade is maximized when p is exactly equal to p star. And the way we show this is by saying that this difference is exactly equal to the integral of fx minus fp from p to p star. And to see that this thing is non-negative, we only have two cases to consider. The first case is when p star is larger than p, in which case, because f as a cumulative distribution function is increasing, so the integrand fx minus fp must be non-negative. And if p star is smaller than f, p star is smaller than p, then fx minus fp is non-positive. And then we flip the sign because the limits of integral, the limits of the integral are flipped. And so in both cases, the point is that the integral is non-negative. Right? And so this proves our result. So a few comments about our result. One easy remark to be made here is that this characterization does not depend on the regularity of f, and in particular, the distribution can be discrete. However, if this distribution has a positive density in the neighborhood of its mean, then we also know that the optimal fixed price mechanism is unique. And one final interesting comment is that dark pools in practice often peg prices to the midpoint of the bid and offer in lit exchanges. And it has been shown that the midpoint here is an unbiased estimator of the mean. Yes, Kira? So dark pools are financial exchanges. So we have lit exchanges, which we can think of as our normal exchanges, and dark pools will be exchanges in which agents trade, taking as given the prices from these lit exchanges. So we're thinking of them as essentially fixed price mechanisms in practice. Okay, so that's our first result. Our main theorem provides an evaluation of the worst case performance of fixed price mechanisms. So theorem 2 states that for any distribution f, the optimal fixed price mechanism achieves at least 1/2 of the first best gains from trade, which we denote by gamma fb. And moreover, we show that this bound is tight. And the way to interpret this theorem is that a priori fixed price mechanisms incur welfare loss due to the Myerson-Satterthwaite impossibility theorem. And in this light, theorem 2 shows that the welfare loss, by restricting attention to fixed price mechanisms, cannot be too large. And in particular, we give a sharp upper bound as to how big this welfare loss can be relative to first best gains from trade. Okay, so let me sketch out a proof of why theorem 2 holds. We want to show that the expected gains from trade under the mean price is at least 1/2 of the first best gains from trade. And one thing that we can do without loss of generality is we can normalize the support of f to be within the unit interval 0 and 1. Now, the observation that we use here is, again, one that expresses the expected gains from trade under the mean price mu as an integral. And we want to approximate gamma fb by gamma mu and show that this approximation must be at least 1/2. Right, so one way to do that is we can maximize gamma fb, which is the first best gains from trade, subject to two conditions. One condition fixes the mean of the distribution. That's the first condition here. And the second condition here fixes the expected gains from trade under the mean price mu. Right, so we're saying that the expected gains from trade is equal to some constant eta here. And this is an infinite dimensional maximization problem. Again, we want to maximize the objective function subject to two constraints. Okay, so one approach might be to think that we might be able to apply tools from standard mechanism design motivated by linear programming. So in this direction, we make a first observation, which is that the constraints here are linear in the distribution F. And moreover, the integrands, one in the first constraint and mu minus x, or rather the positive part of mu minus x here in the second constraint, are both piecewise affine in x. However, we also note that the objective function is not linear in F. And in particular, we can write this out explicitly as a double integral and verify that it is in fact bilinear in F and not linear in F. And so the standard tools of mechanism design motivated by linear programming do not apply here. Right, so what must we do? One other approach is we can observe that the objective function is increasing in the convex order. And so for two distributions, F and G, where F is larger than, we say that F is larger than G under the convex order, if and only if for any convex function V, the integral of V with respect to F is larger than the integral of V with respect to G. In the context of this problem, if F is larger than G in the convex order, then the first best gains from trait under distribution F is larger than the first best gains from trait under distribution G. And the proof of this is simple. In this case, the integrand here in the objective function is the positive part of B minus S, and this is convex both in B and S. Right, so let's go back to a maximization problem. We're faced with this infinite dimensional maximization problem. Instead of maximizing this objective function, we can instead find the maximal F in the convex order. And how we're going to solve this infinite dimensional maximization problem is aided by our key lemma. Our key lemma states that suppose that constraints are linear in F with integrands piecewise affine in X. So exactly as we have them here, then the maximal F in the convex order is going to be a k-point distribution, where k is the number of boundaries of pieces. Yep.
I'm trying to understand the problem you're solving there. So it's the supremum of the first best, right? And then what's the first condition? That shouldn't be like 1, no? Subject to integral.
Sorry, I guess this should be an x. Thank you. Yeah, so the mean of the distribution is equal to mu.
And then this other mu is this gamma mu and
Right, so the second condition here is that the gains from trait under mu. So we're writing the gains from trait under the mean price mu. This is exactly this integral here. So we're maximizing the first best gains from trait subject to the mean being mu as well as the expected gains from trait under mu being eta. Yeah, thank you. Good, so what does the key lemma say? It says that we can restrict attention to k-point distributions, where k is the number of boundaries of pieces. And so let me unpack the latter statement, the number of boundaries of pieces. So in the first case, there's one piece that's x. Thank you for the clarification. There's one piece, x, which has boundaries at 0 and 1. So that's one piece and two boundaries, 0 and 1. And the second condition has two pieces, namely mu minus x from 0 to mu and 0 from mu to 1. So there are two pieces with three boundaries, namely 0, mu, and 1. So the number of boundaries of pieces in this constraint set is going to be 0, mu, and 1, and so k is equal to 3 in this case. And so it's sufficient for us to restrict attention to 3-point distributions. And so this allows us to simplify from an infinite dimensional maximization problem into just a 3-dimensional maximization problem. Okay, so let me give you some geometric intuition for why this lemma is true. Here's a visual example of a distribution denoted here by probability masses in blue. What we want to do is we want to increase this distribution in a convex order fixing the mean of this distribution as well as the expected gains from trade. And the way we do that is we take the point mass. Here we take the point mass at 0.2, and we're going to split it into 2 equal pieces and drag these 2 pieces apart. So that's what I've done here. We have stopped here because one of the pieces has hit one of the boundaries, in this case 0. So this procedure fixes, obviously it fixes the mean of the distribution. It fixes the second integral because none of these pieces have crossed the boundaries. And finally, it also increases the distribution in the convex order. And the intuitive way to see this is that this procedure increases the variability of this distribution, and that happens to increase the distribution in the convex order as well. So we can repeat this procedure. Here I've taken the point mass at 0.4, dragged it apart, and stopped here because one of the pieces has hit 0.7. And we can repeat this indefinitely. And in the limit, we'll get a 3-point distribution. And so this sort of geometric picture tells you why you can restrict attention to just 3-point distributions concentrated at the boundaries 0, mu, and 1. Okay, so that simplifies our maximization problem. So we restrict attention to 3-point distributions, and solving a 3-dimensional maximization problem is easy, so I'll skip the details and instead just state the worst case sequence of distributions. So the worst case sequence of distributions consists of 3-point distributions that is mostly concentrated at the mean of 1/2 and has vanishingly small mass at 0 and 1. Okay, so what I've described to you shows theorem 2, but in fact exactly what I've described to you also shows a stronger version. Here I've stated it as theorem 3. It says that the expected gains from trade under the optimal fixed price mechanism is bounded below by this product. This product consists of a factor that depends on the first best gains from trade, as well as mu, which is the mean of the distribution, and 1 minus mu. And so to see that this is a strengthening of theorem 2, we can take a Taylor expansion of this product, and that gives what I've written down below. And in particular, each of these terms is going to be non-negative, and the first term, which is the first order expansion term, gives the result stated in theorem 2. So before I conclude, I'd just like to relate this paper back to the extant literature. It's mainly related to 3 strands of the literature, namely in robust mechanism design, the bilateral trade problem in mechanism design, as well as convergence in large markets. I would like to just highlight the work of Liad Blum-Rosen and Shahar Dobzhinsky, whose paper in 2014 basically sparked a line of literatures that looked at this problem in different contexts. So to summarize, our results can be understood in the light of the question, why are fixed price mechanisms used in practice? The answer that the literature provides is that fixed price mechanisms are dominant strategy incentive compatible and so strategically simple for agents. And our paper supplements this picture by showing that fixed price mechanisms are simple to design and also have good worst case performance as well. So in the context of bilateral trade, the mean price is optimal and guarantees at least 1/2 of the first best gains from trade. And in the paper, we explore corresponding results for large markets as well. That's the end of my talk. Thank you.
Questions while the next speaker is up?
Yeah, here.
So did you look at, for non-identical distributions at all, and not necessarily the optimal fixed price, but just fixed prices that do well for non-identical distributions approximately?
Yeah, so for asymmetric, okay, so to repeat the question, this was a question about asymmetric distributions and corresponding results in the literature. I think the paper by Blum-Rosen and Dobzhinsky explore asymmetric distributions. One of the results that they find is that the approximation can be arbitrarily bad if we are approximating gains from trade. So I think in their paper they study approximation ratios that consider the total welfare of agents instead of gains from trade, and they give an approximation ratio of 1 minus 1 over e. And in our paper we show that 1 minus 1 over e, we can improve on this bound of 1 minus 1 over e, but this improvement is really small. So it's still an open question as to what the optimal approximation ratio is. Thank you.